Welcome to the Complex Science and Dynamic System Theory online tutorial series. This tutorial of 10 modules is presented to you by the Advanced Consortium of Cooperation, Conflict and Complexity, the Earth Institute at Columbia University. This is Module 1. In this first module, we will learn about the development of complexity science within the context of scientific development. We will see how science suggests that we cannot understand ourselves, human society and the natural universe without complexity science. We will first see how the progression of Western science have created the need for the study of complex phenomena, introducing complexity science. Next, we will introduce you to one of the natural complex phenomena, a flock of birds, and then look at how such complex phenomena appear in all branches of modern science. Finally, we will present you with further resources for in-depth exploration and with a short quiz to recapture the learning from this module. For thousands of years, scientific thinking had tried to explain the reality around us, to predict the consequences of events, processes, and human actions. It has organized human knowledge and enabled human progress. Especially in the last 400 years, being the backbone of the modern age of enlightenment, science had branched into various scientific disciplines, such as the physical sciences, life science, and the social sciences, which developed almost independently. However, since the middle of the 20th century, the different branches of science observed similar problems that they could not explore. This was the time when science started to identify complexity as a common underlying property of these problems. Let's use this animation made by Hannah Fry in her TEDx talk that she gave in UCL on July 2012. To make it simple, complexity problems are the problems that traditional science could not solve. A game of billiard is a good example. Science can help us know where the balls will be at any given time, where would they go, and where would they hit. Same in the solar system. If we look at the planets as the balls in a billiard game, we can know where would they be at any given time, how would they orbit around the sun, and what would be the relations between them. But if we scale the number of objects in the problem to millions and even billions, we're in a different place. Science can explain the behavior of millions and billions of molecules of air behaving together as gas. But what happens to any phenomenon between the billiard balls and billions of molecules? In 1948, an American scientist, Warren Weaver, published an article titled Science and Complexity, in which he made the observation that science has dealt with the two extremes of problems, leaving a huge, unattended middle. This middle region is where complexity science lies. As Weaver anticipated, complexity science has developed during the last 65 years, identifying complex phenomena in many of the scientific fields and creating interdisciplinary and new computing ways to explore them. Let's see now one of such natural complex phenomena. Wow, how about that? When looking at the flock of birds or the school of fish, we are looking at complex systems, which have many interacting parts. The study of this complex system has been recognized as a new type of science. While the living world is a great place to find examples of complex systems, where the actions of individuals turn into the behaviors of groups. So complex systems can be found in the natural and the human world. But what makes the study of these systems important? Biologists, physicists, engineers, mathematicians, and social scientists are finding that the rules that create ordered systems from individual behaviors are showing up in many different scales and disciplines. Let's get back to Hannah Fry's presentation at the TEDxUCL. Scientists in UCLA have made a research in 2008 looking at the crime hotspots at the city. They found how the balance between burglary activities and security measures creates a dynamic of crime, which turns out to be exactly the same as how the leopard gets his spots. Except, in this case, the dynamics of a chemical process that creates the pattern, hence called morphogenesis. Scientists know a lot about the morphogenesis of leopards, so it can be suggested that this knowledge be used to create better crime strategies for the inner city. We leave you now with some suggestions for further reading. And if you continue with us in this tutorial series, we will explore more of the basic principles of the complex and dynamic systems. Please take a moment to answer these very simple and not complex questions to capture your learning from this module. The sources for this module have been taken from these online resources. Thank you for joining this online tutorial. You can visit the rest of the modules in the link attached.